Today we're going to look at work and how we transform energy from one form to another. So we're going to identify the forces involved in transforming one form of energy to another and how we calculate that energy and how much of it is transformed. Okay, in physics, the definition of work that we're going to be using is a little different than the standard English definition. A lot of times we use it saying, work is being done or the people are working. But in physics, work is the energy that is converted when a force is applied in the direction of an object's displacement. Okay, notice that in the direction has been italicized, okay, because it is only the force that is in the direction of the object's displacement that's going to be important. Okay, the formula that we're going to be using is work is equal to the force, the parallel component of force, times the distance. When I say parallel, okay, it's the component of force that is in the same direction as the object's displacement. Okay. Work is a type of energy, so it'll have the same units as energy, or joules. Okay, so when we calculate work, okay, work is going to be force parallel times the distance. If I have multiple forces acting on an object, each force does work, okay, and I can calculate the net work done on the object, okay, by adding up all the individual works, or by simply taking the net force and multiplying it by the displacement. Remember though, it's only the parallel portion, okay, the portion of the forces in the direction that the object moves. So this is the tricky part, okay, in that work will only be performed when the object moves. If the object doesn't move, or if the object has zero displacement, effectively it implies that nothing happened. There was no work done, okay. So also check that the force you are investigating has a component or a portion of that force is in the direction of the object's displacement. So this is the way we're going to be using our formula, okay? Force parallel is not that useful. To calculate the component of that force in the direction, we use force times the cosine of theta, where theta is the angle between the force and the displacement. For example, if this is my force and this is my displacement, then this would be the angle theta. It's the small angle between the two. Okay, or actually it's it's a small angle between the two. So our formula, instead of saying work is equal to force parallel times displacement, though you could say that, this is pretty much the format that we're going to be using it in. Okay, work is equal to force times its distance times the cosine of the angle theta. Okay, many times our theta is going to be 0, 90, or 180. So we should know that cosine of 0 is 1, cosine of 90 is going to be 0, and cosine of 180 is going to equal -1. So let's look at a situation. I have a 5 kilogram block that's being pushed by a 2 Newton force at a constant speed. It's constant speed, so there's a resistive force. Okay, so if I draw a free body diagram, I'm going to have the force of gravity going down. There's a normal force. Okay, there's the force applied, and we'll just call it the force of friction. So all 4 of these forces do work on it on this block as it moves at 4 meters. So let's calculate the work done by each individual force and the net work done on the block. Okay, so the force of gravity, okay, that's just m times g, that's its magnitude. Displacement in this case is 4 meters, and the angle is cosine of 90 because my displacement is in this direction. Okay, and the angle between them is 90. So gravity does no work in this case because cosine of 90 is 0. So it doesn't matter what m, g, and d are, it's still going to be 0. Same with the normal force, okay? The angle there is going to be 90. So m times g times d, it's the same thing, 0 joules. Those two forces are perpendicular to my displacement, and so they do 0 work. My applied force, however, is the one that's doing most of the work here, or is doing positive work. It's pulling my block in the direction. So it's 2 newtons for 4 meters times the cosine of 0. It's done 8 joules as this block is being dragged across the floor. Friction, however, is in the opposite direction. So if I look at the angle there, it's going to be an angle of 180 degrees. Cosine of 180 is -1. So friction does -8 joules. Basically what it's saying is that friction is taking energy away from my block. Okay, if I add them all up, I end up with 0 joules, and that makes sense because my net force on this block is 0 since it's moving at a constant speed. So my net force times any displacement in any direction is still going to be 0. This is a key theorem that we're going to be using, okay, which is the work kinetic energy theorem, which says that the net work done on an object is equivalent to the change in the object's kinetic energy. Okay, so this equation here, okay, that says the net work is equal to the change in the kinetic energy is equal to force times distance times the cosine of theta. This is very similar to our momentum impulse that says force times delta t is going to equal impulse, which is equal to change in momentum. Okay, except in this case, my delta p, okay, is going to be change in kinetic energy, work instead of impulse, and force times distance times the cosine of theta. Okay, I haven't come up with a nice mnemonic on this. Maybe somebody could help me on that. Okay, but the net, and so it basically allows us to compare change in kinetic energy to forces, just like we had change in momentum to the forces being applied. Okay? This is the derivation. Again, this is a proof. You don't need to know it. Some people like it. Okay? Starting from kinematics, we have the formula that has Vf squared is equal to Vi squared plus 2 times acceleration times distance. If I multiply both sides by mass, I end up with mv squared plus mv equals mv squared plus 2mad. If I divide throughout by 2, I then have 1/2 mv squared is equal to 1/2 mv squared plus mass times acceleration times distance. Well, mass times acceleration is just force. So if I end up with the equation below that, rearranging it so that force and displacement is on the left. Okay, and I end up with force times distance is equal to 1/2 mv final squared minus 1/2 mv initial squared, which is just the kinetic energy. So at the end, force times distance is equal to work is equal to change in kinetic energy. Okay, so how do we apply this? Okay, we'll see situations like this where I have a 5 kilogram block which is initially coasting at 10 meters per second. Friction slows the block and the block comes to a stop in 50 meters. Again, these are things that we can measure fairly easily, 50 meters, okay? The momentum of it, okay? Calculate the force of friction acting on the block in this case, and then calculate the coefficient of friction. Well, because I know its initial and final velocities, I know its initial kinetic and final kinetic energies. My initial kinetic energy, just 1/2 mv squared, turns out to be 250 joules. The block comes to a stop, so my velocity is 0, or my final kinetic energy is 0. Well, the work that friction did on this then is final minus initial, or minus 250 joules. So force of friction is the only force that's making it slow down, and that acted on it for 50 meters, so the minus 250 is equal to the force of friction times 50, or the force of friction turns out to be minus 5 newtons. Okay, or 5 newtons in the negative direction, slowing me down. Okay, mu on the other hand, okay, remember the formula that says force of friction is equal to mu times the normal force. We'll assume this is on the level ground. So then mu is equal to the force of friction divided by the normal force. It's a 5 kilogram block. Using 10 as my g, I basically end up with a mu of simply 0.1. Okay? Thank you.